Hello, those watching this online. I'm David, the coordinator of the Maths Learning Centre here at the Uni of Adelaide. This is Semester 2, 2024, and this is the revision seminar for Statistical Practice I. And I've been asked to talk about Z-test, T-test, ANOVA. And I just want to check some things. Every statistics course, like most disciplines in the university, have their own statistics course. You've got one, and there's one in economics, and there's one in education, and there's one in nursing, and they're all just a little different. And also this course has the tendency to change a little bit each year. And so I just want to check what our list of tests is. So I know what ANOVA is, cool, but I have a question. In this course, have they covered two-way ANOVA? Okay. Oh, and also, just a second, do you use R in this course, RStudio? Okay, cool. That's just good to know. Yes. Okay. So this was in the course, but not on the exam. Okay, so they mentioned it in passing, so you don't freak out when you see it in the future, but they're not going to put it on the exam. That's what your lecturer said. Okay, cool. So I'm going to take that as word, but worth checking if you don't, if you're not sure, just go into the Piazza or whatever they use in this course and ask just to be sure. Okay, thank you so much for that information. Okay, so with the t-tests, I'm almost certain that you would have seen at least two flavors of t-test. There would have been a paired one. Is that right? And there would have been, they probably called it the two-sample t-test or the independent samples t-test. Which one? Yeah. It's also in other courses called the independent samples t-test. Okay. I have a question as well. Have you seen this word pooled in reference to t-tests? You have? Okay. You haven't. Okay. So I may just want to look that up in a minute, to be sure. Maybe. But some people have seen it. Okay, cool. Just checking. I will talk about it when we get there. And with Z-tests, in most courses with statistics, there are Z-tests that go with means, and there are Z-tests that go with proportions. Did both of those happen in this course? We don't have the phrase proportion, the word proportion doesn't sound familiar. You do them both? Okay. I might just pause the recording for just a second and ask someone to show me their My Uni so that I can just have a quick click around just to make sure, because I don't want to tell you things that aren't in your course. So just let me pause the recording. Okay. All right. So I've just thank you very much. Had a look at someone's My Uni, just to have a quick check of what's in there. And I think I'm all right now. Oh, damn it. I didn't check this one. That's okay. We'll get there. Okay. So I have one last thing to check. What would make you feel better about these things? Like, they're obviously things that are on your mind. I'm just going to give you some options and you can give me one that isn't those options. But some students, what makes them feel uncomfortable about these is that there's so many of them and they have trouble remembering which bit goes with which one. And sometimes they have trouble reading an exam question or assignment question situation and figuring out which one of them they're supposed to do. And sometimes people just have this overall feeling about them and going, oh, I'm just like the whole thing. I just feel overwhelmed. Does anyone have any of those feelings? Okay, good to know. All right. Okay, so if I'm just going to do the count, we have 1, 2, 3, 4, possibly 5, 6, 7, 8 tests here, approximately. And that seems like a lot. They each go with different kinds of situations. And so it's important to know what features of the situation help you to tell the situations apart. I'm a twin. My twin brother and I do not look the same. We're not identical, but people still don't know which name goes with which twin. Because they don't, well, mainly because my parents would say, this is Paul and David. And they would not say which name goes with which person. But also, even if they know at some point which one was which, they forget what features make us different from each other. And so that's what's going on with this. And so I thought maybe I should start with that. But I'll try and talk about all the details along the way. Yeah, we've got an hour and a half or so, an hour and 40 minutes to go. So I'll see what I can do. One more thing to check. Are you allowed to make a sheet of notes to take with you into the exam? Okay, good. That's good to know. Because the way that you study it will be slightly different if you're allowed, if you can look things up. Okay. Well, first, let me just talk about the concept of tests. Some courses call them hypothesis tests, and some courses call them significance tests. I didn't have a good check of what your lecturer called them. They probably called them both in this course. But the important word is tests. And what statistical tests do is help you decide answers to yes or no questions. That's what tests are for. And so when you are reading an assignment question or doing real research, and you think about your research question, you think about what they've told you about what the researcher wants, if it's a yes or no question, then that's when you would do a test. There are other kinds of questions. Some questions are, what is this number questions? That's what confidence intervals are for. And some questions are, how are these things related? Which is what regression is for. So just while we're on the topic. That's what confidence intervals are for. And that's what regression is for. Just so you know. But both of these can be pitched as yes or no questions if you want. If you have the question, are they related? That's a yes or no question. And you can do that with a test. The test is part of regression. And is the number equal to 5? That's a yes or no question. So as opposed to what's the number? Is the number 5? That's a yes or no question, and that's what a test is for. I just wanted to point out that they are the possibilities. And one of the answers, either yes or no, depending on the way you ask the question, is called the null hypothesis. If you ask your question right, it will be the answer no that you're looking for, but it depends how you ask the question. If you ask the question along the lines of, is there a difference? Then the no answer goes with the null hypothesis. So And that's the usual vibe of how all of these things work. So is there a difference between my number and the number 5? The answer no would be the null hypothesis. Is there a difference between the numerical outcomes in these two different situations? And the answer no would be the null hypothesis. Does this measurement make a difference to this measurement? And the answer no would be the null hypothesis. That's usually, if you can pitch your question in your mind as, is there a difference? Then the no answer goes with null hypothesis. And null means nothing in Latin. And so that's why it goes with the no answer in this context. Okay. And then there is a procedure that you go through to produce a statistical test, and all of your statistical tests will follow the same procedure. Sometimes your lecturer will ask you to do all of it at once, and you have to fill in, just know what the steps are supposed to be. And sometimes they will specifically ask you about each step separately. But the steps are this. So step 1 is to make a null hypothesis. And also an alternative hypothesis. Which is the other answer. The null hypothesis is no, the alternative hypothesis is yes. And that's step 1. But when you do that, in order to write the null hypothesis down using maths, because these are mathematicians really, you can think of this as, is there a difference in your head, but you have to write it down as maths. And so when you write it down as maths, then you have to choose letters to be the numbers that you're thinking about that you don't know what they are. And so along here, you do have to, I'll do examples so that you can see it, but you do have to say what the letters stand for. And I call them letters, but your lecturer will call them parameters. Have you read or heard that phrase where you say, define the parameters that you use? Yeah, that is part of this first step of defining the null hypothesis. You have to say what the letters stand for. So for example, if you reference the letter mu, then you have to say what mu stands for today. Maybe today it's the mean height, maybe tomorrow it's the mean blood pressure, systolic blood pressure, maybe tomorrow, the next day it's the mean weight of the chicks in the experiment or whatever. So like you have to say what they stand for. And then the next step is to choose a test statistic. It's called a test statistic because it helps you do a test. And a statistic is something that you calculate from the data. That's what a statistic is. Anything that you calculate from the data is a kind of statistic. And when they say choose a test statistic, what they mean is write down the formula for how you would calculate that. Cool. Now, the thing is, the philosophy of hypothesis testing is that you imagine that you are living in the land where the null hypothesis is true. And you think, look, if there really wasn't a difference, if being in a different group didn't make a difference to the outcome, if it wasn't different, if the weight of my ice cream containers was not different to what it was last month, if that really was true, how surprised should I be at the data that I collected? That's the big idea. So actually it's like the big idea that we're trying to get at is how surprising is my data? That's the question that we're going to try and ask. How surprising is my data if the null hypothesis is true? That's what we're trying to do. And we're going, hey, cool, I think the mean of my amount of ice cream in my tub should be 2 liters, like it says on the box. And that's what it was last month, but I bought a new machine now, and I've measured them all, and they're all coming out as 2.1 liters. Should that be surprising if it really was still 2 liters or not? That's the question that we're going to ask. Oh, I've got this, when I give them the drug, their score on the depression scale is 50 out of 100. And when I don't give them the drug, their score out of the depression scale is 70 out of 100. If the drug didn't do anything, how surprising is it that they're 20 apart? That's the sort of question that we're asking when we do null hypothesis testing. It's about the level of surprise. Okay. So the thing is, probability is a description of your level of surprise. Probability is a comparison between what you've got and all the things that could have happened. And you're only surprised if it's really quite different to all the things that could happen. And so the only way to figure out your level of surprise is to know all the things that could have happened. And that's what a test statistic is for. You can do a special calculation, and if you do it in just the right way, then it is possible for you to know all of the things it could have been. And that is what a distribution is. So step 3 is to know what the distribution of the test statistic is if the null hypothesis is true. And a distribution is usually a name. So when you first learn the word distribution in this course, it meant have a look at the graph, tell me where the center and the spread and the outliers are. But now in this context, distribution means give me a name. Tell me it's normal, or it's a T, or tell me it's a Z, or it's a T, or an F, or something like that. That's what you need to tell someone. And so your statement will look something like, you know, the test statistic is distributed as a T with like 331 or something like that. That's the sort of statement that you make. Have you seen this twiddle symbol used in this context before? Yeah, okay, good. And so that's an example of the sort of thing that you would say. And here's the thing. The reason we chose the formulas for the test statistics that we did choose is so that we could make this statement. If we had chosen a calculation that we didn't know what its distribution was, we wouldn't be able to do the next step. So the reason the calculations are chosen the way they are is so that we can know the distribution. That's the whole idea of this. And statisticians work very hard with their probability theory to figure out what the distributions of various calculations could be. Okay. How are we feeling? I'll go through all the examples, but I just want to be sure that this is the process. And here's the thing. Different situations with the way your data is structured and the kind of question that you're asking will dictate different test statistics and therefore different distributions. So then the last step, well, the second last step, is to figure out how surprised you are. This is where the level of surprise is. So in my head, this is the surprise part. I'm just setting up to know what all the things that could be are. So the distribution is all the things that could be. That's what I think of that as. The next stage is to knowing all the things it could be and knowing the thing that I did in fact get, how surprised am I? Okay. Just a second. Before we need the value of the test statistic. And so you actually use that formula to actually calculate a number. So this is the number we got from our data. And now we have to ask, how surprising is that number? And usually we go, well, I would be even more surprised if that number was even bigger. And so I'm going to just actually say, how surprising is it to get a number this high or higher? That's what we do. So the last stage, this is the bit where I'm saying, how surprised am I? you calculate a p-value. And the p-value is your level of, it's the opposite. It's not your level of surprise. It's actually your level of unsurprise. It's like, if the p-value is high, you're going, yep, not surprised. I'm okay with that. The lower the p-value is, the more surprised you are. So the p-value is your, what's the opposite of surprise? Boredom. How bored you are about this. That's a boring number. Anyone could have gotten that number. Yeah. How bored you are. That's fun. I've never said it that way. That appeals to me a lot. So the p-value, and usually you'll draw your distribution and maybe it will look like this. And you'll get your test statistic that you got and you'll color in all the ways there are to be further out than that, and you'll get a probability number. E.g., you'll get P is like 0.031 or something like that. Does your lecturer have a preference for how many decimal places a p-value is? Don't know? Okay, some lecturers do. The American Psychological Association has a preference for 3 decimal places. So if you ever do psychology in the future, then your psychology lecturers will dock marks if you don't use the correct number of decimal places. But I think this lecture is a bit more chill than that. So, and then you go, the last step is to decide your answer to your question. Because the whole point was to decide yes or no. And so the lower this number is, the less bored you are and the more surprised you are. And so if this number is very low, then you declare, whoa, I'm really surprised. And so I don't believe that the null hypothesis is true. But if the number is very high, you say, yeah, totally could have happened if the null hypothesis was true. Maybe it is. Now, you don't say it that way, but that's the idea. It's like your answers are null hypothesis is not true, or maybe the null hypothesis is true. But you never 100% reject the, like, you don't, do they use the word retain in this course? Retain, yeah. You either reject the null hypothesis or you retain it. So if P is low, then reject H naught. Who's going, this is boring if the H naught is true. Totally possible. That's the other way around. This is surprising if H naught is true. And if P is high, retain the null hypothesis. And that is how it goes. And then technically step 7 is to say the actual answer to the actual question you wanted. You don't say, as your final thing, I reject H naught. You say, Lecture Theatre gave up on me, in case you're watching the video and going, what the hell are you talking about? What are you doing, David? Technically, your final step is to give an answer in context. So if your original question was, you know, is my new ice cream machine keep producing the same value as the old one, and you retain the null hypothesis, your final conclusion would be, so we retain the null hypothesis and conclude that there is not enough evidence to suggest the new machine is different to the old one. Something like that. Or you say, we have strong evidence to suggest that the new machine is different to the old one and is in fact producing more or less or whatever. So this is the process. It's got 7 steps, but some of those steps are really short. This step number 3 is literally like 1, 2, 3, 4, 5 symbols. And this step is writing down the formula. And this step is usually only a few symbols. Each of these steps is very short. The longest one is probably this one. Actually, the one that has the most symbols in it is the answer in context. It's a full sentence. That's how hypothesis testing works. And every situation is different because of this bit. Which test statistic you choose is all dependent on the kind of data you've got and the kind of question you're answering. So you need to know how to tell which test statistic goes with what situation. Many lecturers base it on the null hypothesis and alternative hypothesis you choose. And then from there, the rest flows. That's not actually good enough. There's various bits of information that are required that make a difference to what you're going to do here. So that's what I wanted to talk about. But before I go on with that, I'm just going to stop for a second and have a drink and let you process. How are you feeling about what I've said so far? And would you like to ask any questions about it? That's okay. These look like the kinds of questions that are in your assignments. Is that right? Where they go through and say, what's the test statistic? What's the distribution? That sort of thing. They do ask these questions. Yeah. So some assignment or exam questions will literally say part A this, part B this, part C this. And some of them will just say perform a t-test. And if they say perform a t-test, you will still have to run through all of these options. You won't necessarily give them headings or numbers, but you will do all of them. Because they want to be sure that you know that these are the things that are part of a hypothesis test. Okay. That's a good start. So, I will not necessarily put these in the order they were in the course, but I will do them. And I am going to do the very first Z test I told you first. And the reason I've done that is probably the same as the reason that they've done it. And it's because it was the first one to ever be invented. So hypothesis testing was invented about 100 years ago. All of these tests were invented that you've learned here, other than the Mann-Whitney U test. They were all invented between about 1890 and 1930. In particular, ANOVA was invented in 1925. We are all coming up to the 100th anniversary of ANOVA. Yeah, so that's pretty cool. Z. The Z test for a mean. So there are Z tests that do go with other situations. So you can't just say Z test. You have to say Z test for a mean if you really want one. In context, if they've already mentioned a mean as part of the story, then they just say Z test, then you know which one it is. But the Z test is for a mean. And the situation is that every individual person or object has a number to go with them. That's the symbol for number. Measure a number for each. Have they used the word subject in this context? What are the subjects of the experiment? Yeah. So the subjects are whatever you measure things on. And they could be people or petri dishes or animals or countries or whatever. So you measure a number for each subject. That is the context. And your yes or no question is the mean of all of the numbers that could possibly be measured for all possible subjects ever, is the mean this number? So for example, and then ask, is the mean this number? That's our yes or no question. And so just as an example, you might ask, I did the ice cream one, new machine fills tubs of ice cream. To fill 30 tubs, each has the volume measured in liters is the mean volume to liters like it's supposed to be. That's the general vibe. And in fact, this sort of question was in fact invented in a quality control situation. So yeah, so one of the people who was instrumental in making the t-test for the modern statistics worked at the Guinness beer factory, for example, and he was working in quality control. Fisher, who invented ANOVA, was working in agriculture and trying to figure out how to make the yield of your grain crop higher. Yeah, and then we now use it a lot in medicine and psychology and stuff, but yeah. So that's the general vibe. And so each subject, my subjects are the tubs of ice cream. Each subject has a volume measured, which is a number, and then I'm interested in the mean volume. That's the general idea. And so that's the situation you need to be in. And so one of the features that will distinguish what kind of situation you're in is the information that's written down about each subject. Does each subject have a number of their own? That's one of the questions that you need to know to decide what situation you're in. Okay, so I generally draw this situation as this. All right, oh, damn it. So there's like a tub of ice cream, and I have written down the volume about each one of them. That's the entire information I've written. And that is a number. And I tend to draw a scale on which to measure the number to help me visually see that it's a number. But my question is, about that volume, my question is just, what's the mean? In fact, my question is, actually, does the number 2 liters do a good job at trying to predict what that volume is? Is it a good number for being in the middle of that volume? That's the question I'm asking. I tend to do all these with pictures because it helps me. Okay, so what I am missing one piece of information here that I'm going to need in order to do this situation. You can't know how surprised you are unless you know how variable the measurement could be. If the measurement's really variable, then you'll be less surprised at getting a high number. And so we need to know how variable it is. And so you have to know some number to say the variability, which is what a standard deviation is. And in this quality control situation, you have a pretty good idea of what the standard deviation is even before you start. And so we're going to assume standard is 0.1 liters, something like that. That's a pretty high standard deviation for a quality control situation, but I can't be bothered fixing it now. So it's really important to know for sure if the standard deviation you've been told has been assumed. You just declare that that's what the standard deviation is, or if it has been measured from the data. That's one of the decisions that you need to make. So in this one, it's been assumed. They won't always use the word assume. They may use the word population standard deviation. They may just say the standard deviation is known to be. They may use the word known, but it's just it will be clear that it has not been calculated from the data. That's the idea. And so the thing that we know is that we do know what sigma is. Sigma is the name of the symbol we use for standard deviation. So this picture, if you wanted to have a single number predicting a numerical outcome and you know the standard deviation, that's what a z-test is for. And so you will go, the null hypothesis is that the mean is 2, where mu is the true mean volume for all tubs that could be filled. Something like that. Or you could say in other situations, it's the true mean blood pressure of people who have this drug, or it's the true mean height of university students of this age, or whatever. And then the alternative hypothesis is the opposite answer to this one, which is that it's not 2. Yay, not that hard. And so this bit here where I said what mu stood for, that's the defining your parameters part of that step. You cannot just write mu, you have to say what it stands for. The only time where you can avoid that step if they've previously in the text told you what mu stands for. But if they haven't told you, then you have to define it. It's really important because, well, honestly, it's not that important, but mathematicians think it's important and they give marks for it. So there you go. And then we're going to say that the test statistic, and the way we calculate the test statistic is very common. Most test statistics are calculated with a subtraction on the top of a fraction and then something on the bottom, usually involving a square root. And so we're going to say that we're going to have our sample mean, which was, oh, they didn't tell us what it was. I say they, it's me. But I just want the formula. That thing there. So we take the sample mean, which is traditionally called x bar. We subtract the mean from the null hypothesis. That's why it's called mu 0. We divide by, and it's not S, it's sigma today because we were told a population standard deviation. And you, inside the bottom of the fraction, divide by root n, where n is the sample size. And this is called Z. I believe borrowing from the German word Zahlen for number. So it just means number. And what we're doing is we're saying, well, just a second, we're going to see how far from the mean we are, and we're going to figure that out in terms of standard deviations adjusted for the sample size. And this will always give you, usually, a number somewhere between -3 and +3. And if it's any bigger than that, then it's even really surprising. And so that's that. You don't usually have to tell the reader what any of these things are. And so we know what the distribution in H0 is the standard normal distribution. That's what it's called. Z is always used for the standard normal distribution. And so we have N0, 1. That's the symbols that mean the standard normal distribution. Okay. And cool, that's that step. And then the next step is to actually calculate what that is. And I can't do that until I actually say what the mean is. So I'm going to have to add that there. Sample mean is 2.05 liters. Let's do that. Sorry about constantly changing the original question. I am making this up off the top of my head. Okay. So the value is 2.05 minus the 2 from that, divided by the sigma, which was 0.1, divided by the square root of the sample size, which was that. And that will require me to calculate (2.05 minus 2 divided by 0.1 divided by the square root of 30. 2.738, whatever. I'll use 4 decimal places. It's probably not necessary. Ta-da! And then I would have to look up in the N01 distribution that number. I'll round off. That is a picture of my p-value. The places that are further out are on the axis here, and then the area here is the probability that we want. And the only way to calculate this probability is to get a computer to tell you what it is, because there is no formula for the probabilities under the normal distribution. So the p-value. So if you were in R, you would do P norm. Oh man. Wait, just a second. So it's definitely P norm, because we've got a normal distribution and we're doing a probability. That's what the P stands for. And P norm always tells you the left-hand side. So you put the negative number in, because then that'll tell me this net left-hand bit. And I'm pretty sure you don't have to tell it the 0 and the 1, but I will anyway, just in case. And that would tell me this bit, and I need 2 of those. Yay, that's what R would need to do that. Cool. My calculator, I do have R. It's going to take ages to start. R takes forever to start. No, I'll do it. Let's start R. And I know I've gone a long way on this one, but I just wanted to be sure of all of the steps, just to make sure. Where's R? Where's R? It's right there in front of me. Okay. Okay. Is it working yet? Yeah, here it comes. You can do it, computer. Sure. Hey. I've got all this data that I was using last time I used R. What? R has failed to load. Oh, no, there it is. So P norm. I don't want to. I can't get it to not put annotate there. Sorry, 2 times P norm minus 2.7401. And it gives me 0.006. Sweet. All right. And that number is very low. The traditional cutoff for lowness is 0.05, which is called the significance level. So Be low is not 2 words. Reject, hate, ignore. At the 5% level. And conclude that the machine is filling tubs higher than 2 liters. And I know it's higher because the mean that I got was 2.05, a little bit higher. Technically, you could say conclude that the machine is filling tubs differently to 2 liters, but we know it's higher because of the mean that we have. So this is the final conclusion in context. If we had retained, if the p-value had been higher than 0.05, then you would have concluded that there is no evidence to suggest that the new machine is filling it differently to 2 liters. So something like that. And that is how a hypothesis test works. You have all these calculations, but I did all of the steps there that I needed to do. I told them the null hypothesis, the alternative hypothesis, the formula for the test statistic, just there. I told them the distribution. I did actually calculate the value. I did the p-value. I rejected or retained, and then I did a conclusion. That is how hypothesis testing works. And they will all have those steps. They will either tell you exactly which steps to use, or they will get you to do the whole thing all at once, and you'll have to do it yourself. Or in an exam, they may do part of it for you and get you to finish it off, or start it and then not finish it. Like, you only have so much time in an exam. And there is one final step, which is officially step 0, is you're supposed to check if you're allowed to use this test in the first place, which is technically that you have to have normal distributions to begin with. So all the way back here, you actually need the sample mean to be normally distributed. So there's technically, once you've chosen a test statistic, you have to check if you're allowed to use that test statistic in your context. Yeah, there is like a secret step 2.5, which is check the assumptions. So somewhere in here. And they're usually checked via a graph, QQ plot or something like that. Okay. So that's how a hypothesis test works. And one of the reasons to show you the Z-test in this course is so you can get a handle on how that process works for the very first and simplest of all of the hypothesis tests that have ever been invented. It's the first one to be invented, and it was the simplest one that doesn't require any fiddly adjustments. Okay, but they will all have that shape. It's just that the R code at this bit will be different, basically, and the formula you write here will be different in each step. Okay, so now I'm going to not necessarily show you all of the bits, but I am going to show you what situations they go with. But before I do so, does anyone want to say anything about what I did just there? Or ask anything? Okay, cool. That was a Z-test for a mean. That Z-test for a mean never happens in actual statistical research, because you never know what the real standard deviation is. It sometimes is used in quality control situations, but you can probably assume that if the mean has changed, then so is the standard deviation. So people don't use Z-tests anymore, not since Gossett invented the t-test. And so I'll do that one first. The t-test for a single mean, sometimes known as the one sample t-test. Yep. It's the exact same situation, A one sample t-test is designed when every individual has a numerical value that goes with it. And you want to try and have an idea of what the mean is. But the difference is that you do not know what the sigma is. You calculate the standard deviation from the data. So it's still the same situation. Measure a number for each subject. Ask, is the mean this number? And also calculate standard deviation from the data. That is the situation in which you use a t-test for a single mean. I'm not going to do the whole story. I just wanted to say that's the situation. So when we line these up next to each other, the thing we added to this one was that we got we assumed the population standard deviation. So the difference is they're exactly the same. We measure the number for each subject. We ask, is the mean this number? In this one, we had the assume the population standard deviation, and this one we calculated it from the data. And so what it looks like, you get your null hypothesis looks exactly the same. Does your lecturer use a capital A or a small a? It probably doesn't matter, but over in economics, which is the seminar I did yesterday, they use a capital A. Is not equal to your particular number that you're interested in. And the test statistic is called a T. And it looks very similar to the test statistic from the Z test, but it has one important difference. Here's the Z. Here's the T. The Z uses a sigma, the T uses an S. That's the difference. And the distribution, T is distributed as a T distribution. They just invented the T distribution. And just like a normal distribution, you need to tell it what the mean and the standard deviation is to know exactly which normal distribution it is. With the T distribution, you have to tell it one number, and that number is called the degrees of freedom. It's a very puzzling name. But in this story, the degrees of freedom is whatever n minus 1 is. So if I had 30 tubs of ice cream, I'd put 29 in that spot. If I had 100 tubs of ice cream, I'd put 99 in that spot. So this thing is called the degrees of freedom. Have you seen it's written this way in this course with the twiddle and the T and the brackets? Or possibly just a little one at the number at the bottom, or is it with brackets? That I'd have to look that one up. So some courses do it with just a little number at the bottom like that. No? Okay. And then the p-value is the same. It looks the same. T distributions to the naked eye or to the hand drawn with a pencil look the same as normal distributions. I just, Desmos, if I drew a in my calculator, could just see a difference between the two curves, but I can't with my pencil. So it will still look the same, and you will still get the thing there, except this time the p-value will still be 2 times something, and it will still be a t something, and it will still be a minus whatever your t is. If your t statistic comes out as minus, you don't have to add an extra minus. You need it to be whatever the negative version is of your number, minus the t statistic. And then you'll have to put in the degrees of freedom there. And this will be a t, because it's a t distribution as opposed to a normal distribution. And the computer will calculate a number for you, and then you'll go, oh, above or below 0.05 or whatever the level is, and then you'll make a decision. So once you get past this bit, it's always the same. The whole point of hypothesis testing is to get to the p-value and then always make the same decision once you get there. That bit after this, it's always the same. But this is the idea of how it works. How are you feeling? Okay. I'm going to not do the next thing that was in the course and jump to a different spot. So at the moment, we have that. We okay? Do you need to check something? Okay, confidence intervals. That's I might say that now while I'm at it. But that is technically answering a different kind of question. But just, you know, interlude, confidence intervals for a mean. So confidence intervals for a mean are in the same situation. Every individual has a number recorded on them. But the question is now, what is the population mean? So what is the population mean? Instead of is the mean equal to a specific number, you say, well, what number is it? And you still have the same thing. Sometimes you calculate the standard deviation from the data. Sometimes you get it from the population. And so that depends on what situation you're in. Get standard deviation. Well, assume the standard deviation sigma, or calculate standard deviation S from the data. So this is the opposite question. So the test answers a yes or no question of is the mean equal to a specific number. The confidence interval is the opposite question of what is the number? And so to be fair, you could ask a whole lot of hypothesis tests. You could say, is the mean 2.2? Is the mean 2.3? Is the mean 2.1? Is the mean 2.05? Is the mean 1.9? And you could ask all of those questions, and some of them would get rejected and some of them would be retained. And the ones that get retained, they are the confidence interval. But that's way too hard. You don't want to do that. Presumably a computer could do that. What you can do is you can say, well, just a second. The ones that get rejected would be the ones where this t is too far out. The ones where the p-value dips below 0.05. And so you can work backwards to figure out exactly which t would give you that 0.05 exactly, and then work backwards to go, all right, cool, my x bars, my mu's would have to be within this zone. Like changing this number in the null hypothesis, what would that have? You can work backwards to figure out what that would have to be to make the t give you exactly 0.05. And that's the edges of the confidence interval. And so what you do with this one is you say that the 95 or whatever percentage, it's usually 95% confidence interval for the mean, its n's are the sample mean plus or minus some, do they use Z star in this course? They put a star on the Z? Yeah. Some critical value of Z times S on root n. And I'm just going to compare this to the Z statistic. It has the same pieces. The X bar is there. The sigma on, oh, not an S, this one's a sigma, sorry. It has the sigma on root n. It has the Z as well. All of those pieces are there. What's actually happened is I've done some algebra and I've multiplied both parts by the sigma on root n, and that's what's created the Z times sigma on root n. And then I've subtracted, like switch the mu from one side and the z to the other side, which is what caused this to happen. So it's a rearrangement of this formula because you really are trying to work backwards. You're saying, well, if the z worked out to be this, that would be the very edge of my p-value. And so that's what it is. And this z here is the z that would have, oh, that's a bad normal distribution. Sorry about that. The z that would have made 0.05. Which means that you have to ask the computer what that is. And so your z star is, so p norm takes a z and gives you a probability. Q norm does the opposite. And it always does the probability to the left-hand side. And so if this is 0.05, then this is 0.25, and therefore this is 0.975. Yeah. And this calculation is like where we've got, this is 0.025, 0.025. And so therefore this must be 1 minus 0.025, which is what's producing the 975. Sorry about that. Damn it. It's actually there. You can also, oh, that would be so much easier. You could figure out the negative one and just make it into a positive number. That would work too. So much better. Sorry about that. So this will work. So all of this calculation is what produced that 975. And the reason it's 975 is because if there's 5% on either side, there must be 2.5% at the top, which leaves you with 97.5% at the bottom. That's why that calculation is there. You could also do minus Q norm of 0.025 like that if you wanted. That would give you the same answer. Because the Q norm 0.025 will give you that number, but it's a negative number. So if you add an extra minus, it'll turn it into a positive number. Sorry about that. Yep. Oh, this is a 9. And it came about because this Z has to have 5% on the outside because of the 95% in the middle, which means it has 2.5% at the top, which means it has 97.5% at the bottom. That's where that came from. But you can also just make it 2.5% at the bottom and then make it into a positive number by putting an extra minus. That's the other way to do it. They give you the same answer. I mean, you obviously can't write R in your exam. I have never known a lecturer for this course to expect you to write down R code. Who knows what they'll do this year, but Lou seems like a very nice person. I've never known a lecturer to expect you to write R code, but they might give you R code and expect you to choose the right one. Yeah. With this one, the 95% confidence interval for the mean, the ends of that confidence interval will be x bar plus or minus t star s on root n. And it's the exact same difference between what we had before. When we switched for the z test to the t test, we switched the z for a t and the sigma to an s. Same things happens in the confidence interval. And what this tells you, there's two separate calculations. There's one with a plus and there's one with a minus. And that tells you the two ends of the confidence interval. And so it will still be the same trick with a 0.025 on either side, but it'll be a t this time. And so the t star will be qt. And you'll have to put the degrees of freedom in this time instead of the 0 and the 1. or minus qt 0.025 n minus 1. Whatever is the thing. That's what you have to do. And then the final answer of interpreting a confidence interval is always the same. You know, we are 95% confident that the true mean is between whatever this number is and whatever this number is. And then you should probably not just say true mean, but true mean volume or true mean weight or true mean height or true mean time or whatever it's the mean of. Your lecturers have probably said this multiple times, and it is true. But this is not English. Don't use your own words. Use the sentence frame and fill in the gaps. And to be fair, this is in fact true in all courses. There are many disciplines where there's only a small number of ways to say things and it be correct. If you were in a law degree, you would have to say it the right way or it would mean something else. And so that's how to do a confidence interval interpretation. So if someone says interpret the confidence interval in context, it will be a sentence something like that. But to have a context, you have to say what it's the mean of, otherwise it's just not in context. All right. Does that answer your question about confidence intervals? Does that answer your question? Okay, cool. So what number page am I up to? 4, 5, and then 6. So I've done a thing here that I just want to say that you can do yourself. You can line things up next to each other so that you can compare them. That will help cement them better in your brain, and it will help you know exactly where the differences are, so that you can tell how to tell the difference between them. So I would recommend that. Obviously, this is way much space for your cheat sheet, but I'm writing big. But just even during your study, it's good to just line things up next to each other. Okay. The next one I wanted to talk about is not the next one in your course. It's later. It's the Z-test for proportions. Proportion is the whoa, that is fuzzy. Proportion is the mathematician's word for percentage written as a decimal. I mean, it's not really, it's just the general concept of an amount out of another amount. That's what proportion is. But the situation doesn't necessarily mention the proportion to begin with. The situation is that your subjects, you haven't necessarily written down a number for each subject. What you've written down for each subject is a yes or no answer to a question. Write down one of 2 options for each subject. You might write down whether the person participates in volunteer work or not. You might write down whether they improve their symptoms or not. You might write down whether they prefer Donald Trump or Kamala Harris for the new president of the United States of America. Just has to be 2 options. And you focus your attention on one of those options and ask, what proportion of people or things will have that answer. But you don't actually ask that. You ask, is the proportion that has that answer this number? So for example, you know, 100. I'm not going to use 100. I'm going to use a more memorable number, 94. Students were surveyed and asked if they volunteer or not. So two options. So yeah, sorry about that. 94 students were surveyed and asked if they volunteer or not. Okay, and then I'm going to say that 41 said they did. Do the majority of students volunteer? That's the question. No proportions are currently mentioned, but they are there. The majority is asking, is the percentage more than 50%? That's what it's asking. And there is a proportion, it's 41 out of 94. And so I can get the information I need from here. So my null hypothesis is that the proportion really is 0.5. Theoretically, my question is it more than 0.5? But you cannot ask a hypothesis test question without picking a number. So it has to be equal to something. And my alternative is that it's not 0.5. Technically, I really want to know if it's more than 0.5, but I would be just as surprised if it was less, if it really was 50%. So I'm going to just leave it at that. Okay. My test statistic is a Z again. And it's always a Z for proportion. There's no Z versus T for proportions. It's just Z for proportions always. So here we go. It is P hat, not X bar, which is how we normally do it. It's P hat minus the P from the null hypothesis over, I'm pretty sure it is this. Pretty sure. You'd have to look it up. I'm almost certain that that's what it is. Worth noting that the P0 occurs 3 times in this formula. Can I change the question? Sorry. Oh, no, I'll do that later. I'll do a what if. I'll just do a what if later. I'm going to leave it at this. So we're nearly there. And the distribution in the H0 situation is that it is a standard normal distribution because that is what Z is. So we wouldn't have called it Z if it wasn't going to be that. So the value, so let's see, my P hat is 41 out of 94. which that's what calculated was for. I know it's less than half. Zero 0.4362. And then my Z will be 0.4362 minus the 0.5 over 0.5 times 1 minus 0.5 over 94. I didn't really give myself enough room to calculate. Let's see. Take that answer and, oh no. And I'll subtract 0.5 and then I'll divide it by a big square root. 0.5. 1 minus 0.5 is 0.5 again, and then 94. So I get minus, damn it, David, why then do you always do this to yourself? Minus 1.238. Okay. All right. That's what I get. And so now to do my p-value, here's my minus 1.238 over here. And I am also interested in what happens at over that side. And I need to know what this probability is. And I have to go so it's going to be the p norm of the 0, 1. And the number I have to put in is minus 1.238. And then that'll give me this half. And then if I times it by 2, it'll give me the top half as well. And I will ask R what that is. You can't see it if you're on the Zoom. On the recording. I'm sorry, but I just can't be bothered switching. And I get 0.2157. That's what I get. I mean, I know it's going to be more than 0.05 because 1.96 is the 0.05 mark. That's where it switches over to under 0.05, and I'm not that far yet. So since this is (0.005), I retain the null hypothesis and conclude that there is not enough evidence to decide that the proportion of volunteers is a majority or not, like is 50%. I'm just going to leave it like that. Oh, crap. Proportions is technically not allowed to be written as a percentage, so 0.5. Going to leave it at that. That wasn't the original question that we asked, but that's the answer I have to give up. So if my p-value had been low, I would have concluded that it's under 0.5. Just a second, I just need to I can't answer that now. Oh well. All right, cool. I really should have set it up so that it came out to under 0.05 because I could have had a nice conclusion, but the world just doesn't work that way. Sometimes you've got that. And then, as an interlude, you could ask yourself, well, what is the proportion of volunteers? That's what you would ask now. And that is a confidence interval question. And so when you do a confidence interval, you normally, so that's a confidence interval question. And I will take the pieces of my hypothesis of my test statistic, and I will form them into a confidence interval. It will be this plus or minus this times this. And so I'll go the 95% confidence interval ends will be p hat plus or minus z star times root. Except this is different. Technically, when you ask the question, what is the proportion, you are allowing yourself the possibility that the proportion isn't 0.5. And so you can't use the p from the null hypothesis in your calculation anymore. In the null hypothesis, like in the test statistic, you were living in the land where the null hypothesis is true. And so you were allowed to use the null hypothesis in this calculation here. But we can't use the p from the null hypothesis in this calculation, so we have to use p hat in this calculation. So that's where it differs from how confidence intervals work for means. Because in the test statistic and the confidence interval for mean, you always use x bar and s. But in the one for p's, you have to use the p hat. And so in this case, it would be 0. What was it? 43262 plus or minus the z star. You'd have to go look up your normal distribution to get exactly 0.05, like to get exactly 95% in the middle. But I know what that number is. It's 1.96. What was the n? 94. Oh, wow. So I have to do this calculation with the plus and do this calculation with the minus. Well, that's my emails. Yay. 0.4362 plus 1.96 times the square root of 0.4362 times 1 minus 0.4362, and then like all of that divided by 94. So I've got my top end is 0.536, and my bottom end, I will switch that to a minus because my calculator allows me to just edit that. 0.336. So my confidence interval is those two numbers. The space between those two numbers. So at 95% confident that the proportion of volunteers for all possible students is somewhere between 33.6% and 53.6%. So we don't know if it's a majority or not. And that confirms our previous conclusion. Ooh. Okay. The reason I wanted to do that one here is it's very similar in its vibe. There's one test statistic, you get a confidence interval. There's not much difference between them other than the calculation you do. You still use a Z. And there's only one thing that you calculate from the data, and each individual subject in the data only has one piece of information about them. That's the other thing that you have. And so back here, if I wanted to draw a picture of the situation that this is, what I have is this situation. Each individual just has a yes or no outcome. One of the options. And my question is, this option, is the P equal to a particular number? That's the question I'm asking. This is the story of this data. These boxes here are the options that you put people in, or, you know, fish or petri dishes or whatever they are. But from a picture point of view, it's very similar. It's still the same story where there's one thing measured on each individual and you're interested in a single number being able to predict it. That's the idea behind it. Okay. All right. I warn you, I can go over. If you have to leave because of parking or, you know, you're exhausted or whatever, I will not be offended. Okay. Okay. So that is that. They are 3 of the 8 that we talked about so far. We're nearly halfway. That's great. So my next test will go back to we'll go back to thinking about means, about numerical outcomes. So here's my next one, which is the t-test. What did they call it? The 2-sample t-test? Two-sample t-test. Oh, okay. 2-sample t-test is designed for a situation where you have 2 samples. And each individual subject has a numerical outcome that you've recorded, but they also have a piece of information about which situation they're in. Each subject is in one of 2 situations, and each subject has a number measured. That is the situation that we're in when you're dealing with the 2-sample t-test. And the question you're asking is, does which situation you're in make a difference to the number that you get? That is what the 2-sample t-test is designed to answer. We do it by talking about means, but that's not what the research question in our mind is. And here's a picture of what that looks like. Every individual has a number, and they also have a situation which has 2 possible situations they could be in. And every individual subject is only in one of those situations. Different individuals are in different situations. Some of them are in the same situation, but each one of them only has one. And we want to know, does the situation you're in make a difference to the number that you get? That's my picture of this story. So I call it a situation, but in the data, it will be a variable. It'll be called situation, or it'll be called group, or it'll be called treatment, or it'll be called whatever. So this is what the story looks like. Now, the statistics cannot actually know whether this situation causes this number to be different. That's not what statistics is for. It can only tell you whether it seems to be that the numbers are different when the situations are different. Because it could be the other way around. It could be that what number you have is what's causing the situation to be different, because you might not have put people in this situation. You could have just recorded them, because this could be like your blood pressure at age 50, and this could be whether you have a heart attack by age 70. And this is what causes that, but whatever. So, but that's fine. We're still going to do it this way, because we're going to try and predict this number from this situation. So what you're going to do is you're going to pitch your question as whether the mean is different in those two situations. So you're going to say that the mean in this situation is mu1 and the mean in this situation is mu2. And we're not going to assume whether we know the population standard deviation or not. We've dispensed with that idea. Once we learn after the Z test, we're not going to do that again. And so that's going to cause us to use T's. But things that have numerical outcomes for each individual person or each individual subject, they use T's. So here we go. This is where I need to ask a very important question, which we'll have to look up my uni to answer, whether we have pooled standard deviations or not in this course, which I don't have access to the my uni. I'm just going to pause for a second while we look that up. Okay. So it is a t-test. Your null hypothesis is that the two means are equal, because you have to pitch your hypothesis to be about parameters. So even though the question in your head is, does being in a different situation make a difference to the number? We're now going to say, does being in a different situation make a difference to the mean? Where mu1 is the population mean in situation 1, and mu2 is the population mean in situation 2. Now, you have to do that in context. If they were treatments, you'd call them in the treatment and in the placebo or something like that. If they were different kinds of people, and you would say mu1 is the population mean for domestic students, and mu2 is the population mean for international students, or whatever. Like, you could do lots of things, but you would have to say the context. And then the alternative is that they are not equal. What's the next step? A test statistic. It's a T. Here we go. Pretty sure that's right. So x1 bar minus x2 bar, square root of s1 squared plus s2 squared over n1. One of them's over n1, the other one's over n2, where n1 and n2 are the sizes of the two groups. And the S1 and S2 are the standard deviations of the two groups, and the X1 bar and the X2 bar are the means of the two groups. We have to subtract them because the idea is that if the mean really are equal, then we should get 0 on average. Because if they are equal, you'll get a 0. So that's the idea. And it comes from the distribution T is from a T distribution with some degrees of freedom. Sorry, capital T. It's from a T distribution with some degrees of freedom. But I do not know how to calculate that. There is a wickedly horrible formula that R will calculate for you. This is called the Wold thing. If you don't have a machine to do this calculation for you at this time, you normally choose the lower of one less than the two sample sizes. But it all just check what to write here. You'd have to look it up. It's different in different courses. But I was always taught that if you didn't have the fancy, ridiculous formula that tells you what the degrees of freedom is, then you can say, well, whichever is lower out of n1 minus 1 and n2 minus 1. And then the p-value would be the same. You'll look your t statistic up and you'll do the pt and times 2 and blah, blah, blah. The rest of it's the same. Sweet, that's two sample t-test. What else have we got? So theoretically, that has a confidence interval too that goes with the difference between the means. And there is a two sample z-test for proportions as well. So the situation is similar. So this one, each subject is in one of two situations. Each subject has, how did I say it before? One of two options for the outcome. And you focus your attention on whichever one you care about. So the two options are usually yes or no for the outcome. And you ask, does the situation affect which outcome? That's the question. And so in terms of stories, you've got your situation, which comes in two flavors, and each individual is in only one of those. And then you have an outcome, which also comes in two flavors, yes or no. And that's the story. It's very similar to the two sample t-test situation, except because everyone's in two situations. It's just that in the t-test situation, you've measured a number for every person. And in this situation, you have a yes or no outcome for each person. And it might not be listed as yes or no. It might be listed as Kamala or Donald. But you have to decide which of the two ones you want the proportion. And so we're going to switch, instead of saying, does the situation affect which outcome, we're saying, does the situation affect the chances of getting a specific outcome? Affect the proportion with this outcome. So you got to pick one. So before it was volunteer work that we did. And this time you're tested, so your null hypothesis is that the proportion in situation 1 is equal to the proportion in situation 2. Proportion with the outcome in situation 1, and P2 is similar. And the alternative is that the proportion is not the proportion. And then the formula for the test statistic is definitely a Z, because we called it a Z test. Of course it's a Z. And it's going to have P1 hat minus P2 hat. That's definitely true. And there'll be something on the bottom with a square root in it. Might have to look this one up. Actually, I think I know what it is. Has someone got this handy that they can check? Is that right? Okay. All right. Where this P hat that doesn't have a 1 or a 2 is made by combining all the two groups together into one big group and figuring out the proportion in the big group. It's called the pooled proportion. Where you combine into one group. So just as an example, um, grapes are exposed to smoke or not, and wine is produced. So there are two situations. We have wine that was made from smoky grapes and wine that was made without smoky grapes. 30 people, 30? Sure. Wine from smoke grapes. And 30, do I do 30? Sure. Wine from no smoke grapes. Okay, cool. And for the first group, 10 people liked the wine. For the second group, 20 people liked the wine. Okay, there we go. There's my story. So does smoke change whether people like the wine or not? That's the question. That's the story. So in this story, the two situations is whether you are given smoke grape wine or non-smoke grape wine, and the outcome is liking or not liking. And so I would, in this story, I'm not going to do the whole, sure. So H naught is that P smoke is equal to this P not smoke, where PS is proportion of people who like wine if the grapes had smoke, right? And PN is the same but no smoke. But if you're writing an exam, you would literally have to write both sentences. And then the alternative would be that PS is not PN. I don't like calling them 1 and 2 if they have names. So, and so the test statistic is Z equals, we know what that is. I'm not going to write that down again. But the distribution is 0, normal. Oh, damn it. The distribution is that Z is normal 0, 1. Yeah, we know the distribution. Distribution in H0 situation is that it's normal 0, 1. And the value of the test statistic is, wait, I can't do the value until I figure out what all the hats are. So P1 hat was 10 out of 30 people. And P2 hat was 20 out of, nope, I pulled them S and N, didn't I? Out of 30 people, which was 2/3. And P hat, well, okay, so there's 60 people total, and 30 of them liked the wine. So this is the 10 plus the 20 people, right? That's what you do. You combine them all into one giant group. There's 60 people total, and the number of people total that liked the wine was 30. And so we get a half. And so therefore my Z is, I'll do the N minus the S because that's easier. So I'll do 2/3 minus 1/3 over the square root of a half times 1 minus a half times 1 over 30 plus 1 over 30. Whatever that is, that's what my Z is. Well, 2/3 minus 1/3 is 1/3, so I'll just deal with that. And I'll divide that by a big square root, and under this we've got a half times a half times 1 over 30 plus 1 over 30. It's 2.582. And that number is huge, right? If I did my p-value, 2.582, I will get a number, and that number is going to be way less than 0.05. It's going to be 0.0. Probably 0.001, let's say, ish. And so therefore reject H0 and conclude fewer people like smoky wine. Right, that's the idea. Whoa. I've made up the numbers, but the relationship between how to stop wine tasting bad when there's been bushfires nearby is a real research thing that happens at this university. Yeah, so that's why I picked it. Of course, what they actually do is they try and treat the wine, the grape juice, before they turn it into wine. But yeah, or they try and grow grapes that are resistant to taking on wood smoke smells. So it's an interesting piece of research. Okay. So what have we got? We've done the 2 sample t-test and the 1 sample t-test. We've done 1 sample z-test for means. We've done proportions, and we've done 2 sample proportions. Oh, there's a paired t-test still. Okay, that's the last one except ANOVA. Radio. So I did something very special when I drew this picture, and it wasn't a coincidence, where I put, each person is only in one of those categories, one of those situations? What if every person was in both situations? Maybe not people, maybe subjects. What if instead of measuring their reaction time, some people's reaction time when you gave them alcohol and some people's reaction time when you didn't, what if you measured everyone's reaction time twice, once with alcohol and once without? That's the kind of story we're telling here. So here's the paired t-test. So the situation is the story is every person is subject is in two situations. Every subject is put into two different situations. And a number outcome is measured twice for every subject, once in each situation. So everybody actually has two numbers, one for each situation. So in the other story, each person had two pieces of information. One was the number they got and one was the situation they're in. Still, everyone has two pieces of information, but they're both numbers and each of them belongs to a different situation. And so the story looks like this. Just a second. You're still asking, does the situation affect the number outcome? You're still asking that same question, but the situation is very different. You are still interested in this outcome, which is a number, and you're still interested in the situation, but every individual subject is in both of those situations. That's the difference. And the reason I draw these pictures is it can help me tell visually that these two things are different to each other. This is what the paired t-test is for, this kind of story. But you have to pitch your null hypothesis as being about parameters. And so where is the parameter? There is a mean in each situation, but every person has a measurement in both. And so we have a little extra that we can do. Instead of asking, does being in a different situation affect the outcome? We can ask, is the difference between those numerical measurements for each person, that difference for every person, is it 0? So we're going to change the question so that each individual person has the outcome in situation 1 and the outcome in situation 2. They both have, both of these numbers are recorded for every person. And we are going to calculate the difference between them, which is a new number for every person. That's what we're going to do. Now, actually, if you ask R to do a paired t-test, it'll do all of this for you. But theoretically, you can calculate this yourself. And so now we're going to ask, now that we've gotten rid of the original information about the two different outcomes, we just calculated the difference, like, you know, outcome 1 minus outcome 2 or something like that. X1 minus X2 usually. Then now we're asking, this difference, is it mostly 0? Like, is the difference different? Like, is there a difference? And so we're actually now we're going that this is the question we're asking now. The difference is 0 the best number for describing that difference? That's the question we're asking. So weirdly, the paired t-test is the easiest one to calculate the test statistic for once you've got all the differences, but it takes some serious thinking about what you're doing. But if you want to do, like if you don't want to do all of this stuff, you can just do this and say, everyone's in two situations, it's a paired t-test. I'll make sure that my R knows that I'm doing that. So the test statistic is the mean of the differences. Well, sorry, I didn't do the null hypothesis. Sorry about that. The null hypothesis is the mean of the differences is 0. All right, and we're going to take compare that to 0 and do the standard deviation of the differences divided by root n. And this will come from a t-distribution with n minus 1 degrees of freedom. That's how the paired t-test works. There's a classic exam question that they give you where they say something like, they'll say 30 people were given, had their reaction time measured with alcohol and without. Here are the means and standard deviations, and they'll give you a table and it'll say like alcohol, no alcohol, the difference, alcohol minus not. It'll say something like that, and it'll say like mean and standard deviation, and it'll give you all these numbers. It'll say like, the reaction time is like 3.1 seconds, and this is like 0.2 seconds, and this is like 1.8 seconds and 0.1 seconds, and this is like, if we took 2, it would be 1.1, 1.3, and let's say this one's 1.5. So they'll give you all this information and then ask you to do a hypothesis test to decide if alcohol makes a difference to reaction time. And what you'll do is you'll use these numbers, the ones that go with the difference. You will not use these. And so you'll say that T, the value of the test statistic is 1.3 minus 0 over 0.15 times over root 30. You'll do that. You won't use these ones. You'll use these ones. Yeah. But if this was 30, if this was 15 people and this was a different 15 people, then you would have done like a 2-sample t-test. And you wouldn't be able to calculate the difference for every person because nobody's been in both situations. So that's the story. Yep. And so this would be, we would use the T29 for this one. That is all the tests other than ANOVA. I'm not going to go through all the details of ANOVA, but I do want to at least say what the story is that ANOVA answers. So ANOVA, analysis of variance, as I said, we're coming up to the 100th anniversary of ANOVA. Analysis of variance invented by Ronald Fisher is designed to answer this sort of question. Each subject is in one of several situations, and each has a number outcome. And so it looks like, and you're asking, does the situation affect the number? So it's the exact same question that you're asking when you do a two-sample t-test. It's just that there's more than one situation, more than two situations. And so the story is you have this numerical outcome and your situation has more than two options. And each individual is in their own situation. That's what ANOVA is for, to answer that question. And the null hypothesis is usually something like mu1 is equal to mu2 is equal to mu3 is equal to however many means there are. However many groups there are. And HA is not all means are equal. And the test statistic is an F, which is complicated to describe how you calculate it. It's calculated from that ANOVA table with SS's, T's, and SSE's, and dividing by things and stuff. So complicated. But it does come from the distribution. The F comes from an F distribution with two numbers for its degrees of freedom instead of just one. And this number is one less than the number of situations. So this is number of situations minus one. And this is the number of subjects minus the number of situations. So some people call it G for groups. Yes. So that is F. And once you've got your F statistic, you can look up the p-value in the F distribution in the same way you'll use a PF instead of a PT. But honestly, all of this is provided for you by R when you ask it to do ANOVA. But you just need to go look in the ANOVA table for where the p-value is. And it doesn't answer the question of which mean is different to which mean. It just says, are they all the same or are they not all the same? And so if you want to know, officially, if you want to know whether those two are different, that's technically a two-sample t-test. And if you want to know if those two are different, that's a different two-sample t-test. If you want to know if those are different, you need a different two-sample t-test. And that story where you have to do several of them all at once is called a multiple comparisons. And so you're supposed to follow up your ANOVA with multiple comparisons. So they all have assumptions. One of the big assumptions for ANOVA that allows you to do the multiple comparisons the way that the ANOVA does it is that all of the standard deviations in the three different situations are the same. And that's what causes you to make a pooled standard deviation. And usually what you do is you look at the smallest standard deviation and the biggest standard deviation and make sure that the biggest one is not more than twice the smallest one. So you go biggest one divided by smallest one and see if that's less than 2. Yeah, so there you go. That is all the tests. The important thing is to know what situation do you live in when you do them. So if you're making a sheet for yourself to take into the exam, you can write down the test statistics and the formulas for them, and you can write down the distributions that they go with, and you can write down the assumptions you're supposed to check and how to check them, but you should also write down the situation they go with. And sometimes lecturers in this course or in other courses will provide you a table, but you should add to that table a little bit of text to say what situation they go in. So it's a little easier to tell. I think that will do for today. There are other revision seminars on the Maths Learning Centre website if you can cope with watching more videos for past years. I just gave a link to you in the email. I'm going to stop the recording there.